Which is the best Lewis structure for HCO2H? So if we are drawing Lewis structures, a Lewis structure accounts for all of the valence electrons in a molecule, and you see those valence electrons as either covalent bonds represented by a line, or a lone pair of electrons, which is represented by two electron dots attached to the atom. So if we're drawing a Lewis structure, we need to know how many total valence electrons we have in the molecule and make sure our Lewis structure represents all of those. So we need to know that hydrogen has 1 valence electron, carbon has 4 valence electrons, and oxygen has 6 valence electrons. And we can also connect this to the typical bonding patterns as well. So hydrogen is in the very first row of the periodic table. That 1 valence electron is a 1s electron. So to have a full outer shell, hydrogen needs one more electron. So what we tend to see hydrogen doing is it tends to gain that extra electron by forming 1 covalent bond. So 1 covalent bond. So this is the typical bonding pattern for hydrogen that we will observe in organic molecules. Carbon has 4 valence electrons. It's in the second row of the periodic table, so it's going to follow the octet rule. So to get to 8 valence electrons, what carbon does is it tends to form 4 covalent bonds. Oxygen is also in the second row of the periodic table. It's more electronegative than carbon, so a little farther over on the table, and it has 6 valence electrons. So it needs to gain 2 more valence electrons in order to have a full octet, and it tends to gain those 2 electrons by forming 2 covalent bonds. So these are some common bonding patterns that you will see in organic chemistry. So it'd be really good to just kind of know these, because you're going to see a lot of hydrogen, you're going to see a lot of carbon, you're going to see a lot of oxygen. So you want to get used to their typical bonding patterns. Okay. So this gives us an idea. Seeing 4 covalent bonds on carbon, that gives me a pretty good idea that carbon's going to be a central atom in this molecule. But we want to total up the valence electrons in the molecule. So the total valence electrons is going to come from all of the atoms. So we have 2 hydrogens. They each have 1 valence electron, so that gives us 2 electrons total. We have 1 carbon atom, and carbon has 4 valence electrons. And then we have 2 oxygens, and oxygen has 6 valence electrons, so that's going to give us 12. So the correct structure then is going to have the sum of these valence electrons, which would be 18. So when we draw our structure, we want to make sure we're representing 18 electrons. So what I'm going to do is I'm going to go ahead and put carbon, which needs to form the greatest number of bonds, as a central atom. So we're going to go ahead and put carbon in there. And we have some hints as to how things are attached to that carbon. So it shows us here this hydrogen next to the carbon. So that's a pretty good idea that that hydrogen is attached to the central carbon atom. And then placing these oxygens, we want to be a bit strategic about this. We know that oxygen tends to form 2 bonds if it's going to be neutral. So I'm going to just put the oxygens on for now. And we're getting a structure that's close to this first structure here. So it might be tempting to put the hydrogen down here. The problem then is that we are out of atoms, and we don't have a way to give our oxygens 2 bonds if we do that. So I'm going to go ahead and bridge the hydrogen onto one of those oxygens. And it might take you a bit of trial and error to get there. But let's see what we've done. Let's see how many valence electrons we've used. So we have used, there's 2 in each covalent bond. So 2, 4, 6, 8 valence electrons. And so what we're showing so far is that the hydrogens look fine. They each have 1 bond. That's what we're looking for. This oxygen has 2 bonds. It also needs some lone pairs of electrons in order to have a full octet. So I'm going to complete the octets on these oxygen atoms with our remaining electrons. So as I mentioned, we have 2, 4, 6, 8. That means we have 10 more electrons that we can place. So 2, 4, and then I'll go to the other oxygen atom. So 2, 4, 6, 8, 10. And so now we have used all of our valence electrons. And so we cannot just add in any more. You may be noticing this carbon atom doesn't have a full octet. But we do not have any more electrons. We've used all 18. So the only way that we could get a full octet onto that carbon is if we shared a pair of electrons. So we can take this pair of electrons from the oxygen and share it with the carbon. And so what this does is this will give us a carbon with a double bond to oxygen. And we still have a bond to hydrogen, and then we have the carbon-oxygen bond with another hydrogen on the end. And so we've got a structure now that's got all 18 electrons in it. It should, we can check. 2, 4, 6, 8, 10, and then we'll count the lone pairs, 12, 14, 16, 18. So we do have the right number of electrons in this structure. And another thing to check would be the formal charge. So all of the atoms in this molecule have a formal charge of 0. So to calculate the formal charge, so for the hydrogens, you take the valence number of the atom, so hydrogen has a valence number of 1, and you subtract from it the number of electrons that belong to the hydrogen in the structure. And so what this hydrogen has, it has just one covalent bond. So there's 2 electrons in this bond, but they're shared, so only one of them belongs to hydrogen. So whenever you have a covalent bond, you count just 1 electron belonging to that atom when you're calculating your formal charge. So we have our valence number, we're going to subtract the number of electrons on it, and we get a formal charge of 0. And we could do this exact same calculation for the other hydrogen, and you'll notice it has the exact same bonding pattern. It has just 1 bond, so that's also going to be 0. So I'm going to turn my attention to the carbon atom. And so carbon has a valence number of 4, right? So one of these valence numbers is actually the same as the number of valence electrons that we mentioned earlier. So it has a valence number of 4, and then for each of these covalent bonds, one of those shared electrons belongs to the carbon. So we have 1, 2, 3, 4. So 4 minus 4 is 0. So the formal charge on that carbon is also 0. And then we can do the same thing for the oxygen atoms. So if we're looking at the oxygen, the valence number for oxygen is 6, right? That's how many valence electrons it has. And then if we count the electrons that belong to the oxygen in this structure, we have these 2 covalent bonds. From each covalent bond, 1 electron belongs to oxygen, the other belongs to its bonding partner. So we have 1, 2. And then lone electrons are not shared. So 3, 4, 5, 6. We have 6 electrons belonging to that oxygen. So that has a formal charge of 0. And this oxygen actually has the same bonding pattern. It looks different, but we see 2 covalent bonds, 2 lone pairs, the same as this oxygen. So that's also 0. So this structure has the correct number of valence electrons, all the octets are satisfied, and we don't have any formal charges.